Okay, good afternoon. So our last week of classes, yay, or boo, depending on your perspective. So we're gonna work on, continue to work through chapter 10 on initial value problems and walk through a bunch of examples to show you how this works. So let me just rewind a little bit in order to remind us what we were talking about on Thursday. So we were discussing single step methods for ordinary differential equations. Again, we'll be following the same sequence as for boundary value problems, first ODEs and then PDEs. And we started last time, we didn't get very far, but I introduced the first order explicit method, also called the Euler method. So we have a first order derivative du dt is equal to some function of the independent and dependent variables t and u. And an initial condition, we only need one because it's first order. So u at t is equal to 0, some known value, u0, which is a constant. And then for the first order explicit method, the x marks the spot was at the previous time step. So where we already know the solution. And then we use a forward difference in time in order to move forward to the n plus first time step. So that's the basic idea. We did that. So here is the first order accurate forward difference approximation for the time derivative on the left-hand side. And then we evaluate the right-hand side, f at the previous time, tn and un. And that's, again, because the x marks the spot is at the previous time step. Then, as always, we put all the unknowns on the left and all the knowns on the right in a first order explicit method, and this is why it's explicit. There's only one unknown, and that's un plus 1. Everything else is at n. un, tn, un. Those are all known from the previous time step. So again, this is an explicit method for that reason. All right, so that's where we ended up last time. So let's do an example to illustrate how this works. The generic scenario we looked at here was a du dt is equal to any function of t and u with a given value of u at the initial time. Let's particularize that so that the function on the right-hand side, the f of tu, is minus a times u, and a will be some constant. For now, we're just going to say it's positive. We'll give it a specific value in a moment, but for now, it's just some positive constant. Okay, so then f of tu is minus au. Simple enough. Turns out we can solve this exactly, and that would be good practice. Your Math 252 professor would be very proud of you if you could solve that exactly. Here is that solution. It's u0, which is the initial condition, times e to the minus at. So this represents an exponential decay in time. So time's going like that, u is up. So it starts at u0, at t is equal to 0, u is u0. And then the e to the minus at means that it has an exponential decay as time increases. So it's going to go down something like that. Great, so that's the exact solution. We'll use that for comparison, but we'll set that aside. We're going to pretend like we don't know the exact solution, and we'll go on and get the numerical solution. Okay, so the first order explicit method we already outlined. We take equation 10(5), that's this one right here. We have un plus 1 is equal to un plus delta t times f of tn un. But now f is simply minus a times u. So we have the un plus 1 is equal to the un plus delta t times f of t and un. But again, f is minus a times un, minus a times u, with u being evaluated at the previous time step, so it's un. Once again, there's only one unknown on the left. Everything on the right is known. So here I've just collected the terms together. There's a un in both terms, so I factor that out. So I have a 1 minus a delta t. Remember, a is positive, all times un. So what this gives us, equation 10(8), is it gives us a prescription for how to move from one time step to the next. So if I know the solution un at Tn, then all I have to do is multiply by 1 minus a delta t, and that gives me an approximation for the solution at the next time step, at the Tn plus 1 time step. Simple as that. And then we just keep doing that until we get tired, and then we stop. So let's say a is 2. So if a is 2, then du dt is minus 2u. So now a is again 2, f is minus 2u. So now our exact solution is e to the minus 2t. And then this is that same equation, but now with a is equal to 2. Everything else is the same. So I start off with the initial condition when n is equal to 0, where u is 1. I put that on the right-hand side for u 0. I multiply by 1 minus 2 delta t, and I get u 1. Then I take that value, put it on the right-hand side, multiply by 1 minus 2 delta t, and I get u 2. And I just keep doing that over and over again until I get tired, and I stop. So here's what the solution looks like for delta t of 0.1. So remember, delta t is, that's the time step. So from Tn to Tn plus 1, that's how far I go. That's the step. So remember, we talked about marching. We're marching forward in time. So the step size is how far I march each time, each step forward in time. So I start at t is equal to 0, where I know the initial condition is 1. And then at 0.1, I get a value that's about 0.8, 0.2, 3, 4, 5, and I just keep continuing, marching forward, getting these values that are represented by the dots. Now, the first thing you'll notice, the solid line there is the exact solution. The first thing you'll notice is it does start to deviate from the exact solution. They start out the same because they both start at 1. That's the initial condition. But the approximate numerical solution starts to kind of sag a bit below the exact solution. And that's because this is a relatively large time step. 0.1 is apparently too large. If you look at the error at t is equal to 2, it's 0.006786. And we'll compare that with the case with the smaller delta t. So just remember 0.007 essentially. So if I reduce the time step by a factor of 10, so now I'm taking smaller steps, so they should be more accurate, but I'm taking 10 times as many time steps to get to my final time, in this case 2. So the dots are still the numerical solution, but now you see 10 times as many of those dots, but they are right on top of the exact solution. So whereas a time step of 0.1 is not sufficient to get a good accurate solution, a time step of 0.01, 10 times smaller, clearly is. So it's much, much better agreement. Now the error is 0.0007. So the error is also a factor of 10 smaller than it was for a larger delta t. All of that makes sense given the order of accuracy of the approximation. All right, now we have to talk about numerical stability. I mentioned this last time. So I said boundary value problems, we only have to worry about accuracy and iterative convergence if we're using an iterative method. Now we have to worry about accuracy as well as numerical stability. So in a boundary value problem, there is no issue, there's no such thing as numerical instability because we're not marching in time, but now there is. So let's first look at the accuracy, then we'll look at stability. So in terms of the accuracy, we actually have 2 types of truncation error. In boundary value problems, we just had 1. First order accurate, second order accurate. It came straight from the approximation that we used, the finite difference method. Now we have a local and a global truncation error. Some people call the global truncation the propagated truncation error, which will become clear in a moment. So the local truncation error, that is because of the time step. So if you look back in equation 10.5 here, so this was our prescription for the first order explicit method. And you can see here we have order delta t squared. Now, where did that come from? because you say, oh, wait, it's first order accurate. So let's trace that through. So here we did our first order accurate approximation, forward difference approximation for the first derivative in time. So that's order delta t. And then we multiplied through by delta t, which made this delta t squared. So the local truncation error is this, order delta t squared. That is the error produced every time I take one step. I take one step, I get another error that's roughly order delta t squared. Order delta t squared, order delta t squared. However, the global or propagated truncation error is the accumulated truncation error after a series of time steps. So after I go 100 time steps or 1,000 time steps or whatever number of time steps, the error that I expect to see in my solution, my approximate solution, is given by the global or propagated truncation error. Now, how does that come about? Well, let's say we have a local truncation error of order delta t squared, as we do here. So we have order delta t squared. And then we'll take capital N time steps. And again, capital N could be 100, could be 1,000, whatever. We're just taking a whole bunch of time steps. So that's order delta t times, well, what's N? N is going to be the total time from t0, the initial time, to Tn, divided by the time step. That'll give us the number of time steps that are taken. Well, order delta t squared, one of those cancels with this delta t, and we have an order delta t accuracy. The assumption, of course, is that this time interval from the initial time t0 to t capital N is order 1. So it's 5 seconds, it's 10 seconds, it's 100 seconds. It's an order 1 number. It's not itty bitty small, and it's not humongously large. So in that case, we have the delta t squared divided by delta t to give us the global truncation error, which is first order accurate, order delta t. So it seems like we just went in a circle, right? We started with order delta t, and then we multiplied by delta t, it became order delta t squared. Now we divide by delta t, and it goes back to order 1. In any case, that's why we call this a first order explicit method, because it's only first order accurate. It's only order delta t accurate. Okay, fine, that's accuracy. Now numerical stability. So we've talked about this in a hand-wavy sort of fashion. Now we're going to have to talk about it in a more quantitative, more precise fashion. So the hand-wavy argument is as follows. A numerical solution is unstable, numerically unstable, if it becomes unbounded, so it starts to blow up at large times, while the exact solution remains bounded. In other words, the exact solution is supposed to show exponential decay, or at least not growing, but instead our numerical solution all of a sudden blows up and goes crazy. So that's the result of a numerical instability. So how do we analyze that? How do we determine whether that is happening or not? So let's take a look at the situation we have in front of us, and that is the first order explicit method. And let's think about this from a numerical stability point of view. Okay, so for the initial time, starting with n is equal to 0, to get for the solution for n is equal to 1, we take the initial condition, u0, multiplied by the 1 minus a delta t, and that gives us u1. That gives us the approximate solution at the next time step. Then we do the same thing. This comes over, and we take that value of u with n equals 1, multiplied by the 1 minus a delta t to get a for n is equal to 2. And then that comes over, and we keep repeating this over and over again. But notice what happens. Here we have 1 minus a delta t times the initial condition. I've just repeated it here. Here we have 1 minus a delta t times the first time step, so u1. But u1, well, that's just 1 minus a delta t times the initial the initial condition. So that's 1 minus a delta t squared times u0. And then the next one is 1 minus a delta t cubed times u0. To the power 4 times u0, to the power 5 times u0. So by the time we get to the n minus first time step. That is going to give us an approximation for un, little n is big N, and that's going to correspond to the nth power, the big nth power of 1 minus a delta t times the initial condition u0. Now, why am I doing all this? I'm doing all this because I want to see what has to happen in order for me, when I go from my initial condition u0 to a later value of the solution at a later time, what has to be true for that not to blow up? So this is the key. So if 1 minus a delta t is larger than 1, then every time I take the power, it's going to get larger, right? So I square it, gets bigger. Cube it, gets bigger. Fourth power gets even bigger. Fifth power gets even bigger. By the time I get up to the capital nth power, it's huge. So that's bad. What I want is for 1 minus a delta t to be less than 1, as indicated here, so that every time I square it, cube it, fourth power, fifth power, every time I multiply by another 1 minus a delta t, it's now getting smaller. Take a number less than 1, multiply it by itself, it gets even smaller. Multiply by itself again, gets even smaller. So the absolute value of this coefficient, the 1 minus a delta t, has to be such that it's less than or equal to 1. If it's 1, that's still okay, because I'm taking 1 times 1, which is still 1 times 1, which is still 1 times 1, capital N times, and everything is fine. It's not blowing up. So as long as it's less than or equal to, we're good in terms of numerical stability. Now remember, a here is positive, so this is 1 minus a positive number. Because a is positive, obviously delta t is positive. So 1 minus delta t, 1 minus a delta t is always less than 1. It's always going to be less than 1. All right, well, I'm getting a little bit ahead of myself. So if the absolute value of 1 minus a delta t is less than or equal to 1, that means that 1 minus a delta t has to be between minus 1 and 1. So I do that to get rid of the absolute value. And then I have a 1 here, a 1 here, and a 1 here. So if I subtract 1 from all three, then I have minus 2 is less than or equal to minus a delta t is less than or equal to 0. And then finally, I look at this and I say, oh, I got lots of negative signs. Let me multiply by negative 1. If I multiply by negative 1, that flips the inequalities. The less than or equal to's become greater than or equal to's. Remember that from algebra. And so then I have that 2 has to be greater than or equal to a delta t, has to be greater than or equal to 0. So then you just ask, is that true? Well, let's look at the right inequality. So a is positive, delta t is positive. So yeah, the product is always bigger than 0. So that's fine. Check. Is a delta t always less than or equal to 2? Well, no. Depends on the delta t, depends on the a. So this is the one that I have to be careful about in terms of numerical stability. So if I solve for delta t, that says that delta t has to be less than or equal to 2 over a. Okay, just bringing the a over here to the left-hand side. So delta t has to be less than 2 over a. So depending on what a is, that's the parameter in the problem, 2 divided by that determines the time step that I have to use in order for my numerical solution to remain stable. Remember, this is the first order explicit method. This is not true for all methods. This is true specifically for the first order explicit method. Delta t has to be less than or equal to 2 over a. And I'll show you what happens. We've already seen the solution when it's stable. I'll show you what happens when you have a time step that's too large. So we say that the method is conditionally stable. So it is stable under certain conditions, but not all conditions. If it was always stable, no matter what, we would say it's unconditionally stable. There are no conditions for which it is not stable. But there are conditions for that have to be satisfied to remain stable, so it's only conditionally stable. So first order explicit method is conditionally stable. Have I said that yet? feel like I'm repeating myself. All right, so let's look at our example, the same one we've been looking at already, with du dt is equal to minus 2u and u0 is equal to 1. Okay, so a is equal to 2, f of tu is minus 2u, again, just like before, and u0 is equal to 1. So we've already looked at this. We have the algorithm. Now let's just run it for a delta t that doesn't satisfy this condition. So in our situation here, remember a is equal to 2, so 2 over 2, last time I checked, that's 1. So delta t has to be less than or equal to 1. Now that's a big time step. I've already showed you that 0.1 is not accurate enough. We had to go to 0.01 to get an accurate solution. But let's just see what happens if I go larger than 1. So if I go larger than 1, here's what happens. So at t is equal to 0, it starts out at 1. That's the initial condition. And it's supposed to go like this, right? It's supposed to be exponential decay. But instead, each time step, I have this growing oscillation. So it's oscillating bigger, as we go forward in time, and the amplitude's getting bigger and bigger and bigger. That, of course, is not what happens in the actual solution, and it is exhibiting unstable behavior. So that's typical. You put in a delta t, if it's too large and you get this kind of oscillation, typically that means that it is an unstable numerical method. All right, so that was for a delta t of 1.05, so just bigger than that threshold of 1. Okay, so you can kind of get a feel for how these things behave and what's going on. All right, let's debrief a little bit. There are different methods that you'll see in the books and online. I call it the first order explicit method because that's the most explicit way to describe it. It's only first order accurate and it's explicit. But many refer to it also as the forward Euler method. Euler because he's the first one who came up with this, and forward because we're using a forward difference. Some people call it the explicit Euler method to emphasize the explicit nature of it. When applied to partial differential equations, as we'll see on Thursday, some people call it the FTCS method, and that stands for forward time, central space. So all of these are the exact same method, okay? So don't be too confused by the different nomenclature. The global error is only first order accurate, so only order delta t. So that's obviously not that great. So accuracy is not that great, and stability is not that great. So we actually have 2 strikes against us, 3 strikes, and we're out. This is very typical. I only looked at obviously one differential equation. If we look at different differential equations, it may have different stability properties, but this is very, very typical. So the first order explicit method is typically only conditionally stable. So there is a limitation on the time step in order for this to work. And it is actually quite restrictive. This particular example said, well, it only has to be less than 1. That's not very restrictive. However, if A was bigger, then that threshold would be much smaller. Now, in this case, if f of tu happens to be nonlinear, so this function on the right-hand side, if it happens to be nonlinear, that's not a problem at all. Let's go back and look at it. If it's nonlinear, then my f of tu, in the general case right here, f of tu, well, that's on the right-hand side. If it's a nonlinear expression, that's fine. I just put in the known t, n, and un, and I get the value of ft u. Not a problem. So whether it's linear or nonlinear for the first order explicit method isn't really very consequential, and everything works out fine. So that's one good thing, at least, about the first order explicit method. Most everything else is bad. Okay, let's improve on the stability. So what I'd like, the ideal method would be both accurate, and usually our standard, as we've seen in boundary value problems, our standard is usually second order accuracy, although there's nothing particularly sacred about that. That's usually the standard. So we'd like second order accuracy, and we would like it to be numerically stable. So The first order explicit method, of course, is neither. So let's first fix the stability problem, and then we'll fix the accuracy problem. So to fix the stability problem, we're going to look at the first order implicit method. So now the idea is, here is my nth and my n plus first time levels. They're a delta t apart, so this is Tn, and this is Tn plus 1. So whereas for the first order explicit method, the x marked the spot was at the previous time step, now the x marks the spot is going to be here at the current time step. So we're going to approximate the equation at the n plus first time level. And sure, why not? Let's see what happens. So now we're going to have to use a backward difference in time, because we're going to approximate the time derivative here, which means we're going to have to look backwards. So un plus 1 minus un over delta t, and that's still only first order accurate. It's just a backward difference rather than a forward difference. But now the f of tu, well, that has to be evaluated at the current time level, n plus 1. So let's see what difference that makes. Once again, putting the unknowns on the left and the knowns on the right. So we have un plus 1, that's unknown. Now we have the f of tn plus 1, un plus 1, that has to now go on the left, before it was on the right. So the only thing that goes on the right is the un. United Nations is the only thing that goes on the UN, is the only thing that goes on the right. Joke doesn't work, Castle, if you mess up. Okay, so now we have an implicit expression. I can't just calculate stuff on the right-hand side and get my un plus 1. I now have a un plus 1 here and a un plus 1 here. So I have to solve implicitly for that unknown, implicitly for the un plus 1. This is kind of like in the boundary value problems when we did the tridiagonal case and we had 3 unknowns. So we had to solve implicitly for them all together. This is going to be very similar. So I have actually 2 un plus 1 unknowns now on the left. Of course, it depends on what this f looks like, but nevertheless, things look a little bit different. All right, so let's see how this works. Let's go back to that same example. So du dt is minus au, and u at t is equal to 0 is u0. So same example as before, a is going to be positive. So again, the f of tu is minus au. Everything is the same. Same exact example. But now, using the first order explicit method. So the first order explicit method, on the left I have un plus 1 minus delta t f of tn plus 1 un plus 1. And then the only known thing on the right-hand side is the un. Okay, well, the f of tu, that's minus au. So that's minus plus a times un plus 1. Once again, I have un plus 1 in both terms. So if I factor it out, I have a 1 plus a delta t times un plus 1 is equal to un. Solve for un plus 1, and I now get this. 1 over 1 plus a delta t un. Okay, so in the end, I still have a nice, straightforward prescription for how I go from the solution at the previous time step, un, to the solution at the current time step, un plus 1. I'm now multiplying by 1 over 1 plus a delta t. Okay, so that's different. If you compare that to the equivalent expression for the first order explicit method, that's clearly different, but also clearly doable. But now let's look at it from a stability point of view. So for stability, this factor has to once again, by absolute value, be less than or equal to 1 for the same reason as before. I'm going to take the previous value, un, I'm going to multiply by this thingamajig to get this. If this thingamajig is bigger than 1, then every time I go from one time step to the next, I'm multiplying by a number that's bigger than 1, bigger than 1, bigger than 1, and it's going to grow, 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 grow. So that's bad. That's numerically unstable. If, on the other hand, this thingamajig is less than 1, Then every time I go from one time step to the next, it's going to get smaller, smaller, smaller. So we need that the absolute value of 1 over 1 plus a delta t has to be less than or equal to 1. Again, to get rid of the absolute value, that means this thingamajig has to be between -1 and 1. Okay, so let's ask ourselves, is it? Well, a is positive, delta t is positive, so the denominator is always a number, positive number, bigger than 1. And you're dividing 1 by a number that's larger than 1. So that's always less than 1. So indeed, it's always less than or equal to 1, so the right inequality is satisfied. Check. That's great. Is it bigger than -1? And the answer, well, yeah, because it's always positive. 1 is positive, 1 plus a delta t is always positive. So this number is always positive, which of course is always bigger than -1. So therefore it is unconditionally stable. It is numerically stable for all conditions, for all delta t's. I don't have to worry about numerical stability when I choose my delta t. The only thing I have to worry about is accuracy. We still want an accurate solution, but whereas for the explicit methods, I have to worry about delta t for both accuracy and numerical stability. Now I can choose my delta t only for the purpose of being sure that it's sufficiently accurate. I could have a delta t of 50. I'll get a horribly inaccurate solution, but at least it's stable. So this is good. It's unconditionally stable. So we check. Of the two issues with the first order explicit method, we've solved one of them. We've taken care of the numerical stability problem. All right, some similar comments. There are some different terms. Some people call it the backward Euler method in contrast to the forward Euler method, or the implicit Euler method in contrast to the explicit Euler method. Again, I prefer the first order implicit method name to make it explicitly clear exactly what we're doing. The global error is still only order delta t. It's still only first order accurate, so we have not improved on the accuracy issue. Now, though, notice what happens if f of tu is nonlinear. If it's nonlinear in u, then when I go back to this equation right here, this might be a nonlinear algebraic equation. If f of u is nonlinear in u, then this will be a nonlinear equation. If that's the case, I can still solve it, but I'm going to have to use methods from chapter 5. I have to use something like Newton's method, remember, for solving nonlinear algebraic equations. All right, so that's a little bit of a hit. That's a bit of a cost. So the improvement is numerical stability, but I now have to be concerned if this is nonlinear in U. Again, we've talked about the unconditional stability of this approach. So again, I can choose any delta t I want. As far as numerical stability, I only have to be concerned with accuracy. So this is a general result. I've only looked at one particular equation, but this is generally true for other equations as well. That is that explicit methods are simple to implement, and even if the f is nonlinear, however, they have stability problems. Whereas implicit methods are much, much better in terms of stability. That doesn't mean all implicit methods apply to all equations are unconditionally stable. It just means that the criteria for numerical stability is almost always, in fact, I've never seen a situation where it's not as good or worse than the explicit method. All right, so that's good. Again, we've checked off one of our issues. Now to fix the second issue, which is accuracy, we go to what's called the Crank-Nicolson method, or some people call this the Trapezoid method. Crank and Nicholson. So here's what they said. They said, well, the problem is when you apply your forward and backward differences, of course, they are only first order accurate. So what you need to do is put your X marks the spot exactly between them. So this is going to be a delta t over 2, delta t over 2. So we split the time step right down the middle. And now we're going to use a second order accurate central difference for the first derivative of, in terms of time with respect to time at this central point. So now it is a second order accurate central difference, which is second order accurate in time. Okay, but now you're going to say, wait a second, we're approximating the equation at a point where we don't know anything, nor do we want the solution there. All right, so you're right. So we're going to have to sort that out. So let's just take the left-hand side again for a moment. So this is du dt. So this is now a second order accurate central difference approximation for the first derivative. Fine, that's no problem. Now I need f and, well, I need f as a function of t and u at that point. How can I get it? Well, it's halfway between these two. So why not just take the average? So if I take the average, so I take f at tu un, sorry, f of tn un, so that's the value of f here, add f of tn plus 1 un plus 1, so that's the value of f here, take those two, divide by 2, and I get the average, which is an approximation for f at this point. Okay. Well, that seems reasonable enough. So then let's see what happens. So if I take all the unknowns to the left, all the knowns to the right, so in other words, anything with the un or tn is, well, anything with the un, I should say, is on the right. Anything with the un plus 1 now is on the left. And you say, well, that doesn't look so bad. It's still an implicit expression, but it looks very similar to the first order implicit method. You'll notice the only difference here is this 1/2 factor. Otherwise, it looks very similar. And of course, there's more stuff on the right-hand side, but that's okay because you just evaluate that. You know FTU on the right because those are evaluated at the previous time step, the nth time step, so everything is fine. So it's still an implicit expression, but now, and there's more to calculate on the right-hand side, but now it is second order accurate. So I'm not going to go through the stability analysis for this, but I will tell you what the result is. So first of all, just terminology, as I said, many call this the trapezoid method. Sounds like the method that we used for numerical integration. It's not the same, although it's similar, it's kind of related. So it's partly why I prefer Crank-Nicolson, because then there's no confusion. The global error is order delta t squared. So it is indeed second order accurate. So it's second order accurate, check. What about stability? Well, we'll get to that in a moment. The other question that we have is, well, what about nonlinearities? If f of tu is nonlinear in u, what are we going to do? Well, this is going to be just like the first order implicit method. I will have a nonlinear algebraic equation on the left-hand side that I'll need to solve using methods such as Newton's method. The alternative is to use something like a Runge-Kutta method, which we'll talk about on Thursday. All right. Well, what's the bottom line in terms of stability? The Crank-Nicolson method is, drum roll please, it's unconditionally stable. Great. So I've fixed the accuracy issue. It's now second order accurate, but I have not done any harm in terms of numerical stability. So it is just as numerically stable, if you want to put it in those terms, as the first order implicit method. So now we have a method, Crank-Nicolson, that checks both of the boxes in terms of our wish list. Unconditionally stable, for this particular problem at least, and second order accurate. Now what we're going to look at next is systems of first order IVPs, initial value problems. And I'll show you why we're doing that and how powerful that really is. So we have basically these three tools in our toolbox: first order explicit, first order implicit, and Crank-Nicolson methods. See relative advantages and disadvantages. Oh my, that sure sounds like a concept question. So we know the relative advantages and disadvantages of each of these three for single IVPs. Now let's look at systems of initial value problems. And then next time we'll extend it to PDEs as well. Okay, so let's look at systems of ordinary differential equations, and then we'll actually connect this with higher order equations as well. In engineering, most of our ordinary differential equations that govern the physics that we care about are not first order. Why? Because most of them, a lot of them, come from F equals MA, and A is the second derivative of position with respect to time. So they're almost always second order, not first order. So we need to figure out how can we solve higher order equations, higher order ordinary differential equations. So we'll look at that. But first, let's develop a framework to think about systems of ODEs, because that's what's going to enable us to do this. So if we start with a problem that has one independent variable time, one dependent variable u, but higher order derivatives, the question is, how can I convert that to a system of first order equations of this form? So we'll get to that in a little bit. But for now, let's just define what we mean. So now I actually have capital N dependent variables, u1, u2 through un, but only one independent variable, time, still. So now I have u1 dot, or du1 dt, is f1 function of t u1, u2 through un. So it's still a function of the independent variable and all of the dependent variables, but now there's more than one dependent variable. Same thing for du2 dt, or u2 dot, that's f2, function of those. And then on all the way down to the nth equation. So I have n, capital N, first order ordinary differential equations. We need just as many initial conditions. So we have initial condition on u1, we'll say that's a1, initial condition on u2, that's a2, and so forth up to the nth initial condition un at t is equal to 0 is a sub n. Great. So again, one independent variable and capital N dependent variables. So you can think of it as a vector. So the solution u now is a vector. Okay, so the question is that I posed at the beginning of this section is, how can I take an capital nth order ordinary differential equation and convert that to something we can solve? More specifically, how can I convert an nth order ordinary differential equation to a system of first order equations? I just said a moment ago, I haven't shown you how to do it yet, but I said a moment ago that we can apply these three methods to systems of first order ODEs. We'll discuss that in a second. But the question now is, how can I take a higher order ODE and convert it to a system of n first order ODEs? So it's actually quite straightforward. So here's a situation where I have one independent variable and one dependent variable, but the order of the differential equation is capital N. Great. So I have nth order derivatives, n minus first order derivatives, n minus twoth order derivatives, second derivatives, first derivatives, zeroth derivatives, all the possible derivatives of u with respect to t. Likewise, we have initial conditions on u, first derivative, second derivative, third derivative, all the way up to the n minus first derivative to have the proper number of initial conditions. Okay, so here's how we do the conversion. Remember, I have one dependent variable u. What I want to do is convert this problem to a system with capital N dependent variables. So we're going to start by saying, all right, u1 is equal to the original u. Well, that's simple enough. And then I'm going to say, okay, u2, that's equal to the first derivative, so du dt, or u dot if you prefer. Then u3 is going to be u double dot, u4, u5, all the way down to u capital N, which will be the n minus first derivative. You can see all of these are one less derivative. This is 1, zeroth derivative, 2, first derivative, 3, second derivative, and so forth. So u sub n is the n minus first derivative of u with respect to t. Now, why does that help us? Well, let me show you. What I'm going to do, I'll do this on the next slide, but to prevent going back and forth, what we're going to do is we're going to take this equation and we're going to differentiate it. So this says that u1 is equal to u. So I'm going to differentiate it with respect to time. So that's going to be u1 dot, or du1 dt, is equal to u dot, or du dt. But look here, du dt, well, that's equal to u2. So we'll reflect that in the first equation. The second equation says that u2 is the first root of u with respect to t. Differentiate, so u2 dot will be u double dot, so d squared u dt squared. But u double dot, well, that's u3. And on and on and on down the list, and you'll see what happens for the last one. So here's that first one I just mentioned. u1 is equal to u. So if we differentiate, du1 dt is equal to du dt, but du dt is just u2. So I have du1 dt is equal to u2. So I'm doing a transformation, so I want to have the final form only in terms of my new variables, u1 through un. I don't want to see any u's, only u1s, u2s, u3s through uns. Second equation was u2 is equal to the first root of u with respect to t. I differentiate, so u2 dot is equal to u double dot, but u double dot, well, that's just u3. So again, du2 dt is u3. And we just keep doing that all the way down. When you get to the very last equation and differentiate this, we're going to have dun dt, so un dot, is equal to the nth derivative of u with respect to t. What do we do with that? Oh, that we have right here from the original equation. The nth derivative of u with respect to t is f. So here you have dun dt, or un dot, is equal to the nth derivative of u with respect to t. And that's just from the original differential equation. That's your f. But, oh, remember, I need to write everything in terms of my new variables. I don't want any more u's. So u is u1. du1 dt, well, that's u2. Second derivative is u3. Third derivative is u4. Up to the n minus first derivative is un. So now on the left-hand side, I only have u1s through uns. And on the right-hand side, I only have u1s through uns, no more u's. So again, what have we done? We've taken a capital nth order ordinary differential equation, and we have converted it to a system of n first order ordinary differential equations. That always, always works. Linear, nonlinear, doesn't matter. You can always do that. So you can always take your nth order equation, convert it to a system of n first order equations. Okay, so now all we have to do is figure out how do I solve that system of first order equations, and then I can solve any system of ODEs. Linear, nonlinear, one independent variable, one dependent variable, multiple dependent variables, higher order, doesn't matter. I can do all of these because I'm going to have one filter through which all of these go, which is a system of first order ODEs. All right, so I promise we can do this. Let's do it. Let's show you how to do it. So here is that final system. Well, here's the right-hand sides, the F's. So I'm going to call this F1, this F2, and this F will be the Fn. So you see that here, just in terms of notation. Initial conditions will be exactly what you think. Great, so now we have our first order system of equations. So let's do an example. I now have a second order ordinary differential equation, u double dot is equal to minus u. I now need two initial conditions because it's second order. So u at t is equal to 0 will be 0, and u dot at t is equal to 0 will be 1. So I have an initial condition on the position and the velocity, if u is a position. Okay, so the first thing I need to do is convert this second order equation to a system of first order equations. Here is the exact solution. Again, you can impress your Math 252 professor by showing how to solve 1019 with those initial conditions and get this as the exact solution. Great practice and never a waste of time. All right, so how do we do the conversion? Capital N now is 2. So I'm going to convert my nth order differential equation to n first order differential equations. So that means I'm going to convert my second order differential equation to 2 first order equations. How do I do that? I define a new set of variables, u1 and u2. u1 will be the original u, and u2 will be du dt, or u dot for short. I take my transformations and I differentiate, exactly what we did before. So u1 is u, so u1 dot is u dot, but u dot is equal to u2, so that's u2. The second equation says that u2 is u dot, so u2 dot is u double dot when we differentiate. What is u double dot? Oh, well, that's u double dot, so u double dot is minus u. And then you remember, oh wait, Professor Castle said everything has to be in terms of the new variables u1 and u2, no more u's. Well, what's u? Oh, well, u is just u1, so then it's minus u1. So then let's just write down the final form just to make it clear. So we have u1 dot is equal to u2, and u2 dot is equal to minus u1. So again, one second order equation has been converted to 2 first order initial value problems. The corresponding initial conditions, u and u1 are the same. So u1 at t is equal to is 0, and then u2 is u dot. So u dot at 0 is 1. So therefore u2 at 0 is 1, because again, u2 is equal to u dot. Now we have, this is really a system of 2 equations for 2 unknowns. So you could write it in matrix form if you'd like, and it would look like this. So your first equation is u1 dot is equal to 0 times u1 plus 1 times u2, because u1 dot is equal to u2. Second equation is u2 dot is equal to minus 1 times u1 plus 0 times u2, which again is exactly that second equation. And then here are the initial conditions in vector form. So you can write it in matrix form like this, or you can just write it like this. Both are perfectly fine and exactly mathematically equivalent. Okay, so we could use the first order explicit method, we could use the first order implicit method, we could use the Crank-Nicolson method. So let's use the first order explicit method and see how this works. So now we're going to do exactly the same thing we did for one equation, but we're going to do it for both equations. So on the left, I have my first order accurate forward difference. That's u1 n plus 1 minus u1 n over delta t. And that's equal to u2 n. Put the only unknown on the left. That's u1 n plus 1. Put all the knowns on the right. That's u1 n plus delta t u2 n. And now we have an explicit expression for u1. If I know u1 and u2 from the previous iteration, previous time step, I can get u1 at the current time step. Same thing for the second equation. So u2 n plus 1 minus u2 n over delta t. So that's a first order accurate forward difference approximation for the first derivative of u with respect to t. And that's equal to minus 1, which is evaluated at the previous time step. So again, the only unknown is u2 n plus 1. That's this. Everything else is known. That's u2n minus delta t u1n. So now it's just more of the same. If I know u1 and u2 at the previous time step, I just put those in on the right-hand side of these 2 equations, and I update u1 and u2 at the current time step. Exactly like before, it's just now 2 equations instead of 1. It's just more of the same. Nothing new, just more of the same. It's still only conditionally stable because we're using this first order explicit method. What about the first order implicit method? Let's see how that works. So again, I have a second order initial value problem, second order ordinary differential equation, but now I'm going to apply the first order implicit method. Now, in terms of converting our 1 second order equation to 2 first order equations, it doesn't matter. That's already been done. I don't have to do it again. That doesn't depend on the method. So u1 dot is u2, u2 dot is minus u1. That's exactly like before. But now, for those 2 equations, I'm going to apply the first order implicit method. So now the X marks the spot is at Tn plus 1. Tn plus 1. So I do a first order accurate backward difference, u1n plus 1 minus u1n over delta t. And that's equal to u2, but evaluated now at the n plus first time step. Unknowns on the left, knowns on the right. Once again, I now have an implicit expression for u1 and u2 at the current time step in terms of what's known at the previous. It's an implicit method instead of explicit, just like before. The second equation, u2 dot is equal to minus u1. So that's u2n plus 1 minus u2n over delta t. That's the left-hand side. The right-hand side is minus u1, evaluated at the n plus first time step. So that's minus u1 n plus 1. Again, unknowns on the left, knowns on the right. So I have two implicit expressions for u1 and u2 at the current time step as I march forward in time. So now you can write this as a matrix problem again. So my unknowns are u1n plus 1, u2n plus 1. And if you track this through, this is 1 times u1n plus 1 minus delta t times u2n plus 1 is equal to u1n, which is exactly this. Okay, then the second equation is delta t times u1n plus 1 times u2n plus 1 is equal to u2n, which is exactly this expression. Okay, so these two equations for my two unknowns are expressed here in matrix form. And now I can solve it. I know these are the values of u1 and u2 at the previous time step, so the right-hand side vector is known. The coefficient matrix is known because I know my time steps, my delta t's. So I can solve this, I can take the inverse or do whatever and solve it for u1 and u2 at the current time step. Again, it is implicit. It's now two equations for two unknowns rather than one equation for one unknown, but nevertheless, it's an an implicit expression. So we have to solve that system of equations. It is now still unconditionally stable for the first order implicit method, which is good, makes us happy. Now, what about Crank-Nicolson? So we can do all three. So same equations, here they are, same two equations that are equal to our one second order equation. Now for the Crank-Nicolson method, again, X marks the spot is right in the middle between the previous and the current time step. So we have on the left that second order accurate central difference approximation. So u1n plus 1 minus u1n over delta t for this. And for u2 dot is u2n plus 1 minus u2n over delta t. Again, second order accurate central difference approximation. Then on the right, this is u2. So we have to average the u2s at the nth and n plus first time step. And on the right here, I have minus u1. So again, I have to average the u1s at the previous and the current time step. Unknowns on the left, knowns on the right, and we have a system of equations. So again, in matrix form, it's going to look like before. I now have a 2 by 2 matrix on the right, but I know this vector, so everything is fine. I still know the right-hand side, and I can solve for the u1 n plus 1 and the u2 n plus 1 at the current time level. You notice the 2 by 2 matrix here is different now because it's a different method. So I'm still solving a 2 by 2 system of equations for two unknowns, but the coefficient matrices, the right-hand side vector are different because it's a different method. Okay, any questions about that? It's pretty straightforward. And when you do these, you'll find, oh, it's just tedious, which of course is why you have a computer do it. You don't do it yourself. You set it up on paper, but then you have your computer do it. So it's a lot of tedious calculations that you have your computer do, but it's pretty straightforward in terms of the method, the algorithm that you use to march in time. And it's the same every time. So the solution that I get here goes to the right-hand side, and then I can solve for the next time step. And that goes to the right-hand side, solve for the next time step. So it's literally just the same thing over and over and over again. So once again, we do have this issue with nonlinearity of f's that you have to worry about. We've discussed that before. These are what are called self-starting. So single step methods are self-starting in the sense that I can start at t is equal to 0 at the initial time, and each subsequent step is going to look exactly the same. A multi-step method, when I try to solve the first time step, I only know one previous time step. If I need to know two previous time steps, I don't have it. So multi-step methods are not self-starting. I need to use something else for the first time step, or maybe even the second if it requires 3. So these are always self-starting because I only need to know the previous time step solution to get the next time step solution, and you can do that right from the beginning. So they're self-starting in that sense. Let's look at our 4-spring mass system that we were playing with a bit ago. So that is a second order equation. I've thrown everything else on the right-hand side. Okay, so this is not the way we normally write it as a second order linear differential equation. However, this is the way we're going to write it in order to convert it to a system of 2 first order equations. So in other words, this is the f. It's a function of t, u, and u dot. So the independent variable, the dependent variable, and its first derivative. So those all go on the right-hand side. So those are all now encapsulated in the f. 2 initial conditions, again, on the u and the u dot. So on the position and the velocity. When I convert this to a system of 2 equations for 2 unknowns, again, exactly the same as before, but let's run through it. So u1 is equal to u being the original dependent variable. u2 is equal to the first derivative of u. Then I differentiate both of those. So I have u1 dot is equal to u dot, but u dot is equal to u2. And then the second equation is u2 is u dot. So I differentiate u2 dot is u double dot, but u double dot, that's this. So that's equal to f. That's equal to f. But you'll notice here I have u's. I have to get rid of those. So u becomes u1 and u dot becomes u2. So if I get rid of this stuff in the middle, whoops, I crossed out too much, got a little too excited there. So if I cross out this stuff in the middle, I have my 2 equations for 2 unknowns that only involve u1 and u2. And again, it's always the case that the last one contains the right-hand side of your equation. Here, the last one is the second one because it's second order accurate, but whatever nth order equation you start with, the last equation is going to have that right-hand side there. Okay, so we can solve this now using the same approach that we just did. And here's the solution. We've seen this before. This is for on the Earth. M is 1, K is 1, C is 0.01. C, remember, is damping. F is 1, omega is 0.2. That's this forcing term right here. And U0 is 1, V0 is 0. So that's the initial conditions. So it wibble wobbles back and forth. So that I showed you the solution before, but I didn't tell you how I got it. This is how I got it, solving this system of 2 first order equations using one of these 3 methods. We also had the 2 mass 3 spring system way back in chapter 3 that I used to motivate systems of equations there and also eigenproblems. So remember at the time we used Newton's second law on these 2 masses to derive the 2 equations. And they were 2 second order equations because we have mass times acceleration, which is a second derivative of position, is equal to the sum of the forces. And the sum of the forces are because of the presence of the 3 springs. So we derived these way back in chapter 3. You can look at that. And then we did some analysis to determine natural frequencies that involved the algebraic eigenproblem. We discussed that. Well, so again, now the question is, well, now how do I solve it? Because before we didn't know how to solve it. I just knew how to do some other things to kind of play around with this and get the natural frequencies, but now we can actually solve it. So here's how it works. Notice we have 2 equations now for 2 dependent variables. So 2 second order equations for two variables. I want to convert that to one system of first order equations. 2 times 2 is 4. Two equations that are both second order. 2 times 2 is 4. It's not 2 plus 2, it's 2 times 2. Because 2 times 2 plus 2 is only 4. 2 times 2 is 4. They're different 4s. Sometimes C is so weird. So I need 4 new dependent variables, U1 through U4. U1 is going to be x1, U2 is x2. Those are the positions of the two masses. Then U3 is going to be the first derivative of x1, and U4 is going to be the first derivative of x2. You say, how's this going to work out? So I'm taking 2 second order equations, converting them to 4 first order equations. Once again, I take these and just differentiate them. So I differentiate U1, it's U1 dot. Differentiate x1, that's x1 dot. But x1 dot is U3, U3. U2 is equal to x2, that's this one. So differentiate, U2 dot is x2 dot, but x2 dot is equal to U4, U4. The third equation, U3 is x1 dot, U3 dot is x1 double dot, but x1 double dot, well, x1 double dot, that's this. So bring the m over, and I have this right-hand side divided by m, and I'm going to call that k. Capital K is little k over m. So I have minus 3 cap k x1 plus cap k x2. Then I remember, oh, wait, I don't want x's, I want u's. So x1, well, that's u1. x2, oh, well, that's u2. So again, get rid of all this stuff in the middle, and I have equations for u1, u2, and u3. The fourth equation, same thing. U4 is x2 dot. So U4 dot is x2 double dot. Get the idea here? Same process. X2 double dot, well, that comes from the second equation, divide through by the 2m. And I have a half cap k x1 minus cap k x2. Oh, yeah, right. X1, that's U1. X2 is U2. So then I cross this all out. And now I have, again, 4 equations for my 4 unknowns, U1, U2, U3, U4. 4 first order initial value problems for my 4 dependent variables. So now I have it in the framework that I need. I can solve it using any one of these 3 methods, and we're good to go. So here's the system of equations written in matrix form, and here's a sample solution. So this is x1 and x2. Okay, so that's how we solve those. I've shown you those pictures before, but I didn't tell you how I got them. Now we know how to get them. Okay, we're almost out of time. I'm going to stop there. We'll pick up next time, our last class, and discuss some additional methods for ODEs, predictor corrector and multi-step methods. And then we'll extend these same techniques of first order explicit, first order implicit, and Crank-Nicolson. We'll extend them to partial differential equations as well. Lots of fun to be had on Thursday. Hang in there for a little bit longer. The semester's almost over. All right, see you then.